welcome to our presentation about our Zurich Route Planner. We are Group J, and we're excited to present our project over the past 2 weeks. So first, what method did we use to model the public transportation network? So naturally, upon examining the data, the first thing that came to us was we can model this as a graph, a directed bipartite multigraph. And so we decided to create this natural graph structure where the nodes represent either stations or trips, where a trip is a vehicle journey on a given route at a specific time. And so with this bipartite structure, we then created edges, which are directed in 3 types. The first is station to station. So this represents a walking transfer from one station to another station. And the next is a station to a trip, which represents a departure from a station for a trip. And then a trip to a station, which represents an arrival for that trip at a specific station. So in combination, the station to trip and then trip to station represents one mode of travel, and the station to station represents another mode of travel. And so using this graph, we specifically looked at 30 kilometers within Zurich's main train station in order to allow for possible routes that go a little beyond the 15 kilometers for the start and stop. And I'll pass it off to Ferdinand for specific details about the graph.
So in the end, we had 48,000 nodes and 2.9 million edges. And then we can share something of our code. Here you can see the stops with their name and ID and location, and we have visualized it here. So these are all the stops within 30 kilometers of Zurich main station. And then we have all the nodes. Their count is here. And then for the edges, these are transfer edges from a stop to trip or trip to stop, with the ID of a stop and a route. And then these are the walking edges where it's from a stop to a stop, and the source and destination. And the count for these total amount of edges are here. Then we have the route planning algorithm.
Thank you. So because of this natural graph structure that we created, the first thing that we did was actually, we first did some research into what kind of work is out there in route planning. And one of the things we were inspired by is the connection scan algorithm. And so with our natural graph structure, we found this to be a traversal. So we actually made a traversal algorithm using the bipartite structure because edges represent possible travel options. So we run this as a time step algorithm. So at each time step, we simulate one step of possible travel from a source. So this can be either a transfer or riding public transportation. And so starting from a source which represents the desired final destination, we iterate over the time steps and simulate all the possible routes out to all the other possible nodes. And so each node accumulates the quickest routes to them from a single source. And at the end, we report the top 5 quickest routes from the source to the desired destination. And so looking at the code for just a quick preview of what this implementation is, what we found is that this actually our algorithm represents a message passing network. So we actually implemented it as such using the GraphFrames library. So at each step, each node sends a message containing a packet of the possible routes it can be used to travel to its other neighbors. And after the sending message step, we have aggregation messages. So each node aggregates those messages and comes up with the top 5 quickest routes to it from all of its neighbors that ultimately start at our desired destination.
Then we have the validation method.
In order to make sure our algorithm is correct, we try to test our algorithm using those following example routes that we found from Google Maps that follow the original and the destination pairs within 15 kilometers of Zurich for those following cases.
So the following cases are, we planned a route which is direct. We found a route which includes a train and a bus. We have a route that requires walking to another station. And we have a route that goes outside the 15-kilometer radius. And due to Spark clusters just not being available, as well as the GraphFrame library not being available, we were not able to test our overall algorithm to make sure that it works. However, we were able to run our algorithm in a Databricks cluster. We utilize an example between Zug and Winterthur, where our algorithm outputs one train between these places, We would have validated this with our confidence intervals, but due to limitations on a free Databricks cluster, we couldn't upload any data.
As he mentioned, we were able to upload some of the data as well as the code to a free Databricks cluster just to test that it was able to run. So here it takes the input for the desired origin destination as well as the latest arrival time. So as an example, these are the inputs. And so after running the message passing step, the message passing algorithm, we find that the best route displayed here is to take a transportation, which this is actually a train. So there's a direct train between the two, and you can see the departure and arrival time. And then this is just walking from the platform to the main train station. So you can see that we can get there quickest by taking a direct route. And so we were able to just validate it on this simple route.
So some shortcomings of our solution. So a pro of our solution is that everything but finding the shortest path is pre-calculated. For example, the confidence intervals, public and public transport model, our models are intuitively simple. So it's not really very challenging to utilize our solution. And we made it so that anyone else can just take a look at the code and be able to understand what's happening. And there's a low memory consumption. If you take a look at the other Spark clusters from some of the other groups, some of the clusters were taking like 60% of the overall memory, and our solution does not do that.
But there still exists some cons. The first is that it's a little time consuming and our algorithm will traverse the entire graph. And the second is there would be other ways to factor in confidence. Right now, we don't provide flexibility for changing this.